All right, it is my great pleasure today to introduce Cynthia Sung. Cynthia is the Gable Family Term Assistant Professor in the Department of Mechanical Engineering and Applied Mechanics, and a member of the General Robotics, Automation, Sensing, and Perception Lab at the University of Pennsylvania. She received a PhD in electrical engineering and computer science from MIT in 2016, and a BS in mechanical engineering from Rice University in 2011. Her research interests are computational methods for design, automation of robotic systems with particular focus on origami-inspired and compliant robots. She is the recipient of a 2019 NSF Career Award, the 2020 Johnson & Johnson Women in STEM Squared D Scholars Award, and a 2017 Popular Mechanics Breakthrough Award. Let's all warmly welcome Cynthia Sung.
Great, thank you very much for that introduction, Jim, and thank you all for coming. It's a pleasure to share my work with all of you. I'm going to be talking today about some of the work we've been doing in our group on origami-inspired design and how we can get dynamical robots using folded structures. So just to get us started, we'll start with origami. So origami is the art of folding. Many of you have probably folded paper or something in your lives. This is just a video of a very common fold pattern. It's the flapping crane. This is the first pattern I learned when I was just learning folding when I was 10 years old. And when it turns out, when you fold a piece of paper, you can turn that sheet of paper into some very interesting 3D objects. A lot of really interesting geometries are able to be created through origami. Some of them can even move, as you just saw in this video here. And what you're seeing on the right is the corresponding fold pattern. So you have a flat sheet of paper, and all of these lines on the paper are the folds that you add in through this procedure of repeatedly folding, turning, inverting certain parts of your pattern to get eventually this flapping crane. Now, normally when people think of folding, they think about this. This is more of a kind of hobby / artistic endeavor where we're really trying to get some sort of 3D structure out of 2D paper, and it's mostly about the aesthetics of the structure. More recently, however, origami has started to really make inroads into engineering as a very powerful mechanism for manufacturing different types of structures. So here's just a smattering of different areas where you might see origami-inspired engineering, from architecture, where people are making these folded structures as window shades, to medical applications where we can take tubular objects and then compress them down into small shapes so that we can use them in non-invasive procedures. This is a personal favorite of mine. It's a company that decided they wanted to create cheap and recyclable dorm furniture for students who were not going to be in a space for a long time. And so they decided to cut out cardboard and fold it up and make tables that can actually hold quite a bit of weight and be useful for however long a student is going to be in a dorm. And of course, we can't forget space applications where folding large structures down into small volumes is really important for being able to bring these objects up into space. So in all of these areas, people have found origami-inspired engineering to be a really powerful tool for getting reconfiguration, for creating lightweight structures, for very rapidly creating these structures, because a lot of the manufacturing processes associated with creating 2D objects are very well established. And we wanted to be able to take advantage of these same manufacturing advantages for robotics. So origami-inspired robotics then is basically taking advantage of folding in order to create some sort of 3D robot that can move around and sense and react to its environment. And there's been a lot of work in creating origami-inspired devices. Some of them exist at CMU. And basically the idea here is that we want to take these 2D manufacturing processes and make robots quickly, make them relatively easily, make them lightweight, so that we can use them in a lot of different application areas. in my group, we're primarily interested in really figuring out what are the limits of creating these origami structures. And as a mechanical engineering lab, we're mostly interested in these three questions. Basically, if we want to be able to take 2D sheets and turn them into 3D objects, how do we think about the geometry of the device? How do we think about the kinematics, how the structure is going to move? And how do we think about the mechanics, how the flexibility of the sheet that we're dealing with affects the dynamics of the robot that we've built? And so I'm going to lead you through a couple of the different thoughts that we've had on these different questions. A lot of these questions are still very open and an active area of research by many labs. And so if any of them capture your imagination, it would be awesome for you to think about them as well. But I'll tell you a little bit about what we've learned about them so far. So to get started, geometry, the question of creating an origami robot kind of starts with its shape, right? If we want to take a 2D sheet and turn it into a 3D robot, we need to know what shapes are possible. And this area has a large history of work in it. There's been a lot of origami mathematicians, a lot of computer scientists who have thought about what is it about folding and what kind of constraints does it produce on a particular structure that allows us to decide whether or not a particular shape is possible. And some of the results have shown us that actually any simple polyhedron you want to fold out of a sheet of paper is possible. It might not be very fun, but you can fold it. And if you want your pattern to be simpler, this gets us into the realm of what people call polyhedron unfoldings, then a lot of structures are possible. Some of them are not. Yeah, so basically there's been work that has shown that you can create any simple polyhedron that you want out of folding. And it might not be fun, but you can do it. You can fold that pattern. And if you want the pattern to be a little bit less complex, you can impose constraints in the realm of work that we call polyhedron unfolding. And in this space, we still actually don't know the answer to which shapes are possible or not. We know that many shapes are possible based on a lot of heuristics. We know that there are shapes that are not possible, but the boundary is not actually well known. And through all of these, research, people have developed quite a few software tools so that if you decide that you want to take a 3D shape and turn it into the 2D fold pattern yourself, you can actually access these tools and do that for whatever mesh it is that you want to generate. So all of these analyses are basically based on the idea that a origami pattern is a rigid mechanism. So if you think back to your linear algebra classes or your mechanics classes, or maybe your graphics classes, you've probably all learned about rigid body transformations, right? And analyzing origami patterns is just an extension of that. So if I have a sheet of paper here, and this is the fold pattern corresponding to the flapping crane on the right, then I can analyze it as if all of the faces were rigid and the folds were hinges, right? So a fold on an origami pattern is an axis of rotation, right? If I have two faces that are on either side of that line, then they can rotate relative to each other, which means that if I want to track a point Q and point P and how they move relative to each other in 3D space based on the fold pattern, then I can say that the location of a point P in 3D space is a rotated version of its location in 2D space, right? And this R here is just a rigid body transformation corresponding to rotation around a line, right? Origami patterns are slightly more complicated than the mechanisms that we traditionally think about, because they're also parallel mechanisms and they have a lot of loops, right? So here, if I have all of these creases in this pattern, then those creases impose a constraint on my pattern. And basically what happens at the end of the day is that if I trace along the loop covering each of these creases, then at the end of the day, this product of all of the rotations I've been to need to bring me back to my original location, right? So there are kinematic constraints associated with these mechanisms that result in basically equations like this, where for every loop in your pattern, the product of all your rotations has to be identity. But if you satisfy these equations, then you can do an analysis of your origami pattern and you can figure out exactly what 3D shape your pattern is going to turn into. And you can develop basically algorithms like the Origamizer that allow you to flip back and forth between your 3D and your 2D shape. So here's an example of the output from the Origamizer, which was developed by Tomohiro Tachi. He's at the University of Tokyo. And he was able to take the Stanford bunny shape and turn it into this 2D fold pattern here. This is a video of him folding the rabbit. It took him 10 hours, but you can kind of see the light changing in the background. But at the end of the day, if we fast forward, then you see that the pattern did become this Stanford bunny shape. So what we know then is that if you want to take a 3D polyhedron, turn it into a fold pattern, we can do it. That doesn't mean that what the pattern has come out with is going to be necessarily that useful for the origami robotics. So here I'm including a zoom in version of the pattern that's outputted by that software. And there are a couple of things that I want to note. First is that all of the white polygons in here, so like all of these white triangles, these are what are exposed on the surface of the bunny. All of the gray material in the middle here and on the edge of the square, that's all extra material that gets tucked away on the inside of the bunny. So basically the way these algorithms work is that you have all these triangles on the surface, you spread them out so that they don't intersect on the 2D plane, and then you add in a whole bunch of pleats to tuck away all of the extra material. So you end up with a lot of wasted material. The other thing I want to note is that, well, once we've done this, we know that all of the white triangles are on the surface of the bunny, but who knows which one is which? Finding the mapping between your 2D pattern and your 3D object is not very intuitive with a lot of these algorithms. And then the third thing is that if we are trying to create just a 2D pattern to generate a particular 3D shape, oftentimes the motion of that shape is not included in the pattern design, right? So if I wanted to create a bunny that had wiggling ears, that's not going to happen with a lot of existing origami design algorithms because they just create a static shape at the end of the day. So from the point of view of making origami robotics, we want to be able to address all of these issues because we want our fabrication methods to be relatively efficient. We don't want to waste too much material. We want to make the design process a little bit more intuitive. So we want to know how the 2D pattern maps to the 3D shape. And we definitely want these robots to be able to move. So the approach that we've been taking in our lab is more of a design by composition approach. Basically, if you have a pattern for the bunny and then you have a pattern for the ears and you want the ears to wiggle, then maybe we should, instead of trying to make a pattern for the whole thing, cut up the bunny and figure out which patterns go where in order to make the shape that and the motions that we want. So the idea is like this. If we have a library of designs, all of these are real designs that people have created either in our lab or in other labs. Each of these designs is associated with some sort of high-level representation. So this includes geometry, includes kinematics, how these designs move. And now if I want to create a new design, then I can basically map parts of this new design to parts in the database, right? So here I'm creating a 3-fingered gripper that does not exist in the database, but I know that there is another gripper in the database that I can pull a finger from. Or let's say that I have a translating base, or I want a translating base, and there isn't one in the database, but I know that there's this, I don't know, translating segment of some sort of worm robot in the gripper, in the database. I can pull that in and I can attach them together. And because all of the libraries in the database are associated with real physical designs, I can also turn the new design into a physical prototype, right? So that's the idea. We've basically taken this idea and integrated it into a software tool that we call Build-A-Bot, which allows people to pull shapes from a database, manipulate their geometries based on what they want the structure to look like. They can attach certain parts together, and the system keeps track internally of what the corresponding fold pattern was that was associated with the parts that they pulled in. It also keeps track of geometric constraints on the 3D object and uses a grammar to figure out which of these connections are moving or not. So now a person can assemble a robot and then simulate how it's going to move, figure out how it's going to work on this 2D plane. And if they're happy with it, then because all of the parts in the database were associated with real fold patterns, then the system can automatically generate the structures that we need to fabricate in order to create this design. So in this case, that design that I just showed you in the video turns into a 3D print that we can print the list of electronic components and the software that we put on the robot. And within about 30 minutes following the assembly instructions, we can have that exact robot walking around on our desk. So this, we think, is a very intuitive way to assemble the origami robots. And we've tested it on a couple of different users, told them to make whatever geometry it is that they wanted, or making a robot parade. And they were able to generate a couple of different interesting geometries. All of these are able to be fabricated as, in this case, print and fold structures. And we actually did fabricate a few of them, which you can see here. And for all of them, the parts were generated by the software and printed and assembled in less than 2 hours. So we think that this idea of composing patterns together in order to create more complicated robotic structures is a way to move forward on getting more robot designs that are easier to create and that can be fabricated using this fast and lightweight origami-inspired fabrication method. Now, you may have noticed in the video that I showed you that we kind of cheated in this software in that, yes, we composed origami patterns together, but most of them are composed by snapping them together, right? So we didn't actually generate a single origami pattern for each of the parts on each of these robots, right? We kind of just took all of the parts from the database and then printed them individually, and the person had to put them together. The other thing we cheated on is that, well, actually, at the beginning, I complained that the organizer doesn't create structures that move. None of the structures that we printed out in this demo moved either. All of the motion comes from motors. However, a lot of the origami robots that you do see in the literature can move based on the fold pattern itself. So what we're trying to think about now is also how do we integrate the kinematics of the origami pattern into the design process as well. So the way that we think about this problem then is, again, in the sense of rigid mechanisms, right? So if I have a fold pattern, then a fold is a hinge, right? And if I put a fold in a piece of paper, then I get two flaps of paper that move relative to each other, right? And I can combine multiple folds and multiple faces together in order to create linkages, right? So here, if I take a strip of paper and then I put 3 folds in it, and then I attach the ends together, I get a 4-bar linkage. This gives me coupled horizontal and vertical translation in the plane, right? And I can stack multiple of these linkages together, and I can decouple these different degrees of freedom. So I can take these ideas about modeling origami patterns as linkage mechanisms in order to compose different fold patterns that have degrees of freedom that I might want. So for example, I can take this idea of stacked 4-bar linkages and manipulate it a little bit and get some really interesting joints. So here's an example of that same 4-bar structure that I've now made out of trapezoids instead of rectangles. It's still a 4-bar linkage, but now it's not planar. It's basically a spherical linkage, right? And I can translate this pattern. So I can copy this unit, in this case, wrap it around in a circle, in this case, what this linkage is going to do is have coupled vertical translation with a rotation around the center axis, right? And I can extract this information if I analyze the degrees of freedom of this pattern. If I stack more of these layers on top of each other, again, I increase the range of motion, I can decouple my degrees of freedom, and basically I can create an interesting rotational joint. What I think is really nice about these sorts of structures that we can create by breaking down these origami patterns as rigid body mechanisms is that now you can think about origami patterns as tessellations, and you can also think about the degrees of freedom of an individual unit. And this entire joint here is now also parameterized. So if I want to change its range of motion, I can change the dimensions of an individual unit, or I can change how many units I want to attach together, which gives me a lot of flexibility in designing a particular type of joint for my robot. All right, well, we showed that you can get a variety of different types of joints using these ideas of using origami tessellations. And these joints can give you translation, they can give you rotation, they are all parameterized so that you can map the whatever range of motion it is you want on the 3D device onto the 2D pattern. And so what that means is that theoretically, at least, if you want to create a robot and it has a particular degree of freedom in it, we can generate the corresponding origami pattern, assuming that we can combine the patterns together. All right, so we've also shown in other work that if you have multiple patterns that you do want to combine together, it is possible to generate a one-piece non-self-intersecting composition of two-fold patterns. It's possible in polynomial time with a polynomial amount of wasted material. And to put this in more layman's terms, what that means is that compared to the geometric work I showed you before, now we can not only create any shape through folding, but we can actually also create any mechanism out of one piece of plastic. And so what you're seeing here is an example of a robot that we composed just kind of as a demo. We call it the penguin because we think it kind of looks like one, but basically it has a pivoting base and a 4-bar linkage on top. And this design here and rigid bodies that were in the database. So what you're seeing on the left here is the corresponding fold pattern. And I want to point out some things. One is that all of the faces in the fold pattern are used on the surface of the robot. We don't really have any extra wasted material here in this design. In addition, if you look at the pattern versus you look at the robot, and you know what's in the database, you can map what's on the pattern to what's on the robot. So this entire section here is the pivot joint on the bottom. This part up here is the 4-bar linkage on top. This stuff in the middle is the base that connects the two, right? And so now the makeup of the fold pattern is also more intuitive. Okay. And the other nice thing that, and people often ask, well, you know, this is okay, but also the patterns you showed us before for the 3D printed robots were much simpler than what we're looking at now. One of the reasons that we're really excited about this ability to be able to create the entire robot out of one piece is that it gives us also other manufacturing advantages. So now that we can take these patterns and put them onto one sheet, we can put circuitry directly onto the robot's surface. So here you see that all of the circuits were laid directly onto the body of the robot here. Here's a close-up of what was on, what we put onto the robot. The motors and sensors are soldered directly into the circuit as well. And as an added bonus, I heard some of you mentioning earlier that you probably wouldn't want to fold this yourself. I will tell you that it took me, an experienced folder, 6 hours to fold this thing. as an added bonus, if everything is one piece, it actually makes the assembly a little bit easier because we can also take advantage of a lot of self-assembling methods. So one of the things that we're thinking about in the lab is, yes, a lot of times people probably don't want to assemble their robots themselves. And wouldn't it be cool that if, as we were creating these origami robots, we could pack them into an envelope, mail it off to whoever wanted it, and then they stick it in the oven, bake it for a bit, and they have a robot come out of the oven, right? We can't get to that vision completely yet, but there are some lamination-based approaches that give us some indication that it may be possible to get there in the future. So basically, if you take a piece of plastic and then you sandwich some shrinky dink between two layers of this plastic, and then you cut some gaps into the plastic and you heat the whole thing up, then the structure will fold. And it folds because the shrinking layer encounters a constraint on the bottom layer where there's no gap, and has some freedom on the top layer where there is some gap. So the whole structure will fold in the direction of the gap. This allows you to basically make sheets, fold pattern sheets, put them on a hot plate, and then get them to self-fold within seconds. So like I said, this pattern is relatively simple compared to the one I just showed you. We haven't been able to fully automate the process of folding the entire penguin by itself, but we think that using these automated fabrication techniques and self-assembly techniques, we can possibly get to the state in the future where these robots can be fabricated as flat sheets and then also assemble themselves. In addition, because we can put the circuitry directly on the robot, then this gives us access to a basically uniform process for fabricating and assembling an entire robot.
With origami.
Well, so basically, we have this process now that we're using in the lab where now you can basically put your circuitry and get your robot to self-fold, and everything is basically created through these laminated layers, which you can connect together, and you end up with these sorts of structures that I showed you on the right, which I asked my student to make on first clear plastic, so you could see the top and the bottom and how everything looks kind of when it's put together. We can add in off-the-shelf components if we want to, or we can solder on directly these SMD components. But the nice thing now is that with these sorts of structures, then we can drop them directly onto the robots that I showed you earlier. These are in fact the circuits that were on the ones I showed you before. And everything is also aligned into the 3D shape. So this motor and this sensor were not attached with wires, they were soldered directly into the circuit that we created. So yes, so basically using these sorts of ideas, then we can generate these one sheet robots, these origami patterns for these moving machines with integrated electronics and actuation and sensing that we think hopefully in the future we'll be able to get to self-fold to the complexity required to create these sorts of devices. Okay, so now in the title, I promised that we were actually going to create dynamical robots out of origami, and I haven't actually showed you any of that yet. This is a figure from a Nature review article on origami robotics. And this was basically the survey image that was at the beginning of the article showing the variety of origami robots that are currently, that existed as of 2018. What you'll notice in this and the examples that I just showed you is that all of these robots are relatively small, or that they don't actually carry that much load. And so there's a big question that we've been trying to ask ourselves, which is, well, is it possible to use these fabrication approaches to also make robots that carry load or robots that need to use large amounts of power? Or is there a fundamental limitation to making these robots out of thin sheets? And so more recently, we've started to delve into the mechanics of these origami structures. And primarily, the inspiration is that when we've been folding these structures, the theory tells us that these joints are perfect joints, and they have, the degrees of freedom we want them to have, and they'll work as if they were exactly the type of joint that we might buy from a store that was not made out of origami. But practically, if you measure the force displacement curves for these patterns, then there is some resistance to motion. And this is because all of them are made out of folded materials and not machined as real hinges. And so you can take this data and actually create models for these origami structures to figure out how they're deforming as they move inside of the robot. So one thing that we've done then is try to model the mechanics of an origami fold. And basically, you can model an origami pattern as a spring network. So here I have these two sheets, and they're connected by a fold. This fold here is basically a spring. It has theoretically only 1 degree of freedom along this axis here, which is the fold, but practically it has other degrees of freedom as well. And so if I try to actuate this structure, then the whole structure will deform and it'll settle at the minimum energy state, right? So what that means is that I can take advantage of the compliance of these structures to make moving objects, moving structures. So here again is the Stanford bunny, but instead of folding it using the organizer pattern, what we're going to do is just slice it up, right? And we're going to add folds between each of the layers to create this compliance in the structure. And what I can do also is add some tendons to the structure in order to actuate it. What's going to happen is that the final state of the pattern is determined by minimizing the full energy of the structure subject to the length of the tendons that I pull. And we can optimize the locations of these tendons and the folds in order to get this structure to move in the way that we want it to. So at the end of the day, I can get these really interesting layered patterns that have some very naturalistic motions just because we're taking advantage of the fact that folds are not actually 1 degree of freedom. They have many degrees of freedom. And the sheet itself that we're working with can bend into form. So this bunny here was sliced and folded in the way I showed you above. I think it has something like 5 or 6 tendons in it. This human head was also automatically generated by slicing it and adding folds in particular locations. It has 7 tendons that were placed in order to give it these sorts of motions that it's able to accomplish. And I want to emphasize that these motions really are only possible because origami patterns are not perfectly rigid mechanisms, right? They do take advantage of the fact that the sheets are bending. So that means that we can create really soft structures. We've also demonstrated you can make really stiff structures by using stiffer materials like aluminum that you see on the right. But one thing that we haven't figured out, that I haven't told you about yet, is whether we can bridge the gap between them. So when it comes to origami mechanics, then there's some really interesting properties and results from geometry that tell us about how we can control the mechanics of these structures. So in particular, we draw a lot of inspiration from the Bellows theorem. The Bellows theorem says that the volume of a polyhedron with rigid faces is invariant under flexing. And so what that means is that if you have a pattern that looks like this, and all of the faces are theoretically rigid, in that if we model it as the more traditional way of modeling rigid origami, then this structure is basically fixed. It has no degrees of freedom. It can't move. But practically, this pattern is a bellows. It's basically an origami spring, and it can deform. And the reason why it's deforming is because the faces are bending, and we have degrees of freedom that are not just at the folds. So we can take advantage of these ideas in order to create not just very soft structures, but also relatively stiff structures out of thin shell materials. So if this here is the pattern corresponding to the origami spring I'm showing you on the top right. And again, this is a parameterized pattern where we can change the dimensions of the pattern and the angles of these creases in order to manipulate the 3D design. The shape of the 3D design informs what the mechanics of the structure is going to be. So if you change this alpha angle right here by 1 degree, you move the force displacement curve from these red curves here to this blue curve here. And you go from a device that previously experienced snap through, that means it has 2 stable states, to one that just buckles. And then if you move your alpha angle even more, you end up with some very stiff structures here. So by taking advantage of results like the bellows theorem, we can start to create origami structures that are that span the boundary between very soft and very stiff structures. The way that we model these structures is again as a spring network and by using these energy minimization ideas. So I can take this unit in the pattern, turn it into a spring network here. Each of my folds is a spring. I have a torsion spring corresponding to the folding motion. And then I have a spring down the middle corresponding to the bending of the face. And if I pattern this spring network across the entire pattern, then I can predict that the 3D shape is going to deform in this way and produce this sort of curve. So what that means is that we can now create origami robots that are not limited to small objects or to low load situations, but they can actually carry significant amounts of load and deliver significant amounts of power. Two of the students on this project, Wei-Shi Chen and Shivangi Mishra, decided to fully characterize the relationship between the geometric parameters and the mechanics properties of this particular pattern. And you can see that they span a large range of stiffnesses depending on what the angle of the pattern is. Not only that, but they got very ambitious and decided to cycle this pattern through like 2,000 cycles of stretching and compression. And this is the first cycle here, this red one. This blue one here is the last cycle, and the gray ones are the ones in the middle. You can see that the first cycle was a little bit different. This is a very well-known phenomenon. It's commonly called the virgin fold phenomenon because you're folding something for the first time. But the structure very quickly converges to a steady state behavior close to the blue curve. And these structures are very robust. They last thousands of cycles. And so hopefully, what that indicates is that we can then take these structures and put them into robots that are going to be doing repeated actions over and over again. So this design was then integrated into this dynamical hopping robot, which you're seeing on the screen now. And basically the idea here is that we can now take these origami patterns that are very lightweight, but have designable stiffness in order to create these hopping robots that mimic the hopping behavior of robots created through more traditional means. And what I want to emphasize here is that all the stuff at the top is motors and control board. It's 2.5 kilograms of stuff that we just kind of slapped on top here. We didn't fully integrate all the actuators yet, but we kind of just slapped on top here for the purposes of demonstrating the usefulness of the origami spring. And the spring itself is only 48 grams. That's carrying the weight of the rest of the structure over a lot of repeated jumping maneuvers. And so this robot here has done hundreds of hops at this point. It's still alive, and it leveraging the fact that our origami pattern is not just this perfect rigid mechanism. It does have compliance, and it has tunable compliance according to its geometric parameters. This robot is capable of jumping over a variety of terrain. So in this case, because the structure is compliant, and we put a simple Raybert-styled hopper controller on top of it, you can release it onto a world with some obstacles, and the speed will change, but it will be able to move itself forward reliably because it basically implements the traditional spring-loaded inverted pendulum model of running robot behavior. Because we're able to tune the stiffness of these structures using the geometry, one of my students, Jamie Carlson, got very interested in seeing whether we can control a robot jumping just through geometry and not through control. So in this case, what she did was take that exact same pattern, but only keep one layer. And this whole pattern now can jump. Again, all of the electronics are integrated into the pattern. In this case, we just used servo motors because it was the easiest thing for us to grab, but all of the other electronics are on the top of the pattern, and this whole structure can jump. It can carry its own weight, about 40 grams, up to the height of the robot, which is about 100 millimeters. And what's interesting here is that if you embed multiple states into the fold pattern by looking at different angles of your fold, then you can have multiple stiffnesses embedded into the pattern. And so with the same controller, you can get your robot to jump to either 97 millimeters or to 120 millimeters by choosing a different set of folds to activate. And so in this case, the controller for the jumping robot is the geometry, not the software. All of these ideas we can translate just as much to non-legged systems. So we took these same ideas, we put them on another pattern, we modeled the energy, tried to predict how this whole thing was going to deform. We were able to predict a force displacement curve, which matched the data. And then my students put this origami pattern, we actuated this origami pattern with what they call a spine. And this whole waterproof container protects the electronics so that now this pattern can swim in the water. And so again, this sort of deformation that this robot is going through is dictated by the mechanics of the pattern of the skin. And when the actuators compress the skin, then because of the way the pattern deforms and the way the faces bend, then the robot is able to expand in volume to suck in water and then release it quickly in order to propel itself forward. So basically, the punchline here is that using these mechanics models and origami patterns that don't follow our theoretical models, but instead do take into account deformation of the faces and degrees of freedom that we might normally not want to think about, we can specifically design patterns in order to produce dynamical maneuvers that we want out of these mechanisms. So so where are we going in the future? Basically, the direction that we're moving is towards getting this more unified approach towards robot design and towards specifically origami robot design. And what we're thinking is that although origami robotics has been very promising, a lot of these designs have not taken into account the mechanical properties, and that embedding mechanical properties into these robots is a non-trivial endeavor. And so our idea is that we want to take information about what the robot is going to do, the behavior, the environment, and map that into mechanical or mechanics properties for the device that then we can map onto geometric parameters of our database parts. And we can compose those designs together so that if in the future you want a robot to do a task for you and you want to take advantage of origami-inspired fabrication or lamination-based fabrication technologies, then the mapping from your 3D robot onto your 2D pattern becomes much more straightforward. We're also really excited by this idea that because your pattern is made of a 2D sheet, you can embed the actuation and sensing directly into the sheet itself, and that potentially is a way to reconfigure your robot. So one thing that we've done as kind of a side note that some of you have seen is looked at how we can embed actuation into robotic structures via knitted mechanisms. And so this is an example of an SMA wire that we knitted into a tube. Unlike regular SMA, which gets 5% deformation, this allows us to deform by up to 25%. And it simultaneously works as an actuator and a sensor. So we can track the state of the knit by tracking the resistance of the knit. And so by taking these wires and knitting them into a sheet, we can basically simultaneously deform a sheet and then also put in some feedback control and sense what the, and get to a particular type of deformation. Because all of these knits are also made of conductive material, they're basically short. And so if you apply voltages across different corners of a really large knit, then you can localize heating to particular locations of your sheet and localize deformation to particular locations of your sheet. And so we think that by taking these sort of knitted actuators and adding them into our lamination-based approaches, then we can have active reconfiguration of these, of the robots that I just showed you. Why might we want this? Well, to remind you of the dynamical robot that I showed you at the beginning, this robot can move over a variety of terrains, but that doesn't mean it's good at all of them. And so in particular, when it hits this egg crate environment, it slows down a lot. And we know from existing work in legged locomotion that the ability of a robot to traverse a terrain depends on the robot's stiffness and its damping. So if we can manipulate the stiffness of a device, then we can potentially manipulate the robot's ability to deal with certain environments. And so we've shown that by embedding different fold patterns into a 3D structure, we can get these different stiffnesses. And what I'm showing you on the left here is the work of one of my students, Shivangi Misra, who developed a local stiffness controller to allow us to stabilize a particular configuration in a fold pattern. So looking forward, just to give you an idea of what we're doing next, our idea is that in the future, you will be able to take a dynamical task that you want for a robot, map it onto a fold pattern based on what you want its kinematics to be, what you want its stiffness parameters to be. And you will also be able to manipulate the geometry of the pattern on the fly in order to adjust the mechanical characteristics to the environment that you want your robot to be in. So right now, we think all of the theory is in place and we're implementing it. You should all, if you're interested, you should look forward to the hardware implementation that we are currently making and hope to have done this summer. So with that, that's basically an overview of what we're doing in the lab. Again, we're looking at a lot of different types of origami-inspired structures, looking at questions from what kinds of geometry can we create, how do we actually fabricate these and get them to self-fold, what kinds of joints and what kind of kinematic structures can we create, and then most recently, what kind of dynamical robots can we create to ensure that these origami-inspired fabrication practices have applications not only on small-scale robots, but in a variety of application domains. This work was done by my lab members, both the human and the non-human, as well as through discussions by a lot of collaborators.